Okay. Hello, everyone. Thank you to come to the QBC Seminar. It's the first one in 2025. So it is our great honor to have Professor Thomas Jennewein to be our speaker today. So Dr. Jennewein completed his PhD at the University of Vienna on quantum key distribution and teleportation experiments. After that, he became a senior scientist at the IQOQI of the Austrian Academy of Sciences. In 2009, he decided to come to Canada to take a faculty position at the University of Waterloo Institute of Quantum Computing. And in 2024, so he moved to the West Coast to join SFU as a Canadian Excellence Research Chair for Global Quantum Internet Systems. So Dr. Jennewein's research vision is to build a capable and scalable quantum communication technology for long-range and satellite quantum networks. So he initiated and now leads the Canadian satellite mission called the Quantum Encryption and Science Satellite. So its aims is to demonstrate quantum communication and quantum key distribution between space and ground with stations across Canada and even internationally. So Dr. Jennewein has a lot of great scientific achievement. In particular, he led the first free photon interference, an important fundamental advance for the field of quantum optics. It is recognized as by the physics world as one of the top 10 breakthroughs in 2017. So today he is going to tell us more about the quantum satellite. So let's welcome Thomas.
Great. Hey. Well, great. Well, thank you very much. And I hope sound and everything is good. So yeah, it's my great pleasure to be here and give you like a bit of overview of the quantum communication experiments that I've been working on, and give a bit more of a background story of how we got there from basic quantum optics experiments actually to do this now in space. And yep, let's try this one. Doesn't react. Okay, I'll just put my hand. But I will start off by talking a little bit of just about one of the motivators of this quantum communication, which is secure communication. It actually stems from the development of quantum computers, and here's a picture of the IBM quantum computer, right, which are advancing. And one of the applications of quantum computers is they could be used to decrypt classical encryption algorithms based on Diffie-Hellman key exchange, right, where computational power is the assumption of security. And let's say if you go to a secure website, right, your browser is exchanging keys with the server and to encrypt it. But that is in principle hackable because it's based on an algorithm. And here's the result of a survey conducted by Michele Mosca and colleagues at EvolutionQ, and they found out, or by surveying a list of experts in quantum computing, but also cryptography, they found out that the sort of likelihood that the perception have the people in this community that within 15 years of a time frame, there is more than a 50% likelihood that quantum computers will be able to hack, in this case, they were asking an RSA 2048 key, right? So why is this relevant? Well, if you're sending information today over the internet or encrypted in such an algorithm, this could be stored now and decrypted later. And so what's happening is, well, there is a bit of a threat out there that quantum computers could become available in a not too far future, 10, 15 years, right? And so what you're sending today, you have to be mindful about, right? Because if you want to have long-term security, this could already be a problem. Now, this is one of the advancements or applications of quantum computers. And interestingly, quantum information also offers a possible workaround, which is quantum key exchange and quantum key distribution. So quantum key distribution was developed by Gilles Brassard and Charles Bennett, and there's the famous 1984 protocol, or the BB84, where essentially what happens is that the communication, there's a communication channel between an Alice and a Bob, and by sending particles that are encrypted, that they were assuming qubits, and what we'll be using is actually photon states for that. But anyway, these qubits are sent one after the other, encoded in random information, and because a single particle cannot be measured perfectly without introducing errors, this scheme is secure to establish a key, because if somebody were to try to manipulate or read out those quantum states while they are traveling, it will cause errors that can be detected, right? And that's what this BB84 protocol proposed at the time, and is the basis for this quantum cryptography that we have today. So that in itself is a very interesting situation, right? So quantum information on one side, quantum computers pose a threat, and at the same time, quantum information also offers a possible solution. And I just really wanted to take a really quick detour into, how we got here, right? More than 100 years ago, it was discovered that the black body radiation has issues, right? And Planck famously, in an act of desperation, as he called it, postulated that the radiation is quantized, and was able to, in particular, replicate the spectrum that's emitted, right, based on this quantization hypothesis. And of course, as we know, right, Einstein later was able to formalize this further, and the photon concept was born. At the same, around that time, superposition was discovered and discussed, right? And here's this famous exchange between Bohr and Einstein about wave-particle duality, and how is that even possible, right? So if we have photons, which are particles, how should they replicate this interference pictures? This famous, this famous Gedankenexperiment, which at the time was a thought experiment, and today in the lab we can take pictures like this, which was taken with a single photon array, detector array, and these are individual photon clicks as they were accumulated in such a double slit experiment. And by accumulating it more and more, one can see this interference picture build up, right? So this is very well established today and widely known. And of course, this superposition principle states that for a particle, it can go in both paths at the same time. It's path A or path B, and if there's no information whatsoever about which path it takes, then we get interference, right? And this is exactly the underlying security, the reason of security for quantum key distribution, because as soon as an eavesdropper is trying to measure the state of a superposition, right, of where the particle is actually passing through. Now, in the example of the double slit, it means which slit it's passing. This is like reading out, extracting information. This causes the interference pattern to get diminished or even disappear. So there's this trade-off between visibility and which way information, right? And exactly this concept translates to quantum key distribution in terms of security. So Alice and Bob are essentially measuring the quality of superposition states that are sent over this channel to tell if the channel was pure or preserved the superposition states or failed them, right? Or they got degraded. And I also like to point out that the superposition principle translates to multiparties as the entanglement, right? Where the superposition essentially can also describe not just the states of one particle, but also multiple particles. So these are all of the essential building blocks of quantum information, and I'm still very amazed, that those basic philosophical discussions from more than 100 years ago, they now, form a baseline all of this quantum technology revolution that's happening, right, 100 years later. And essentially, there's this famous quote about, paying bills, and it does indeed pay a lot of our bills, right? This quantum technology. So, what else can we learn from that? Well, if you engage in philosophical discussions about some, seemingly abstruse theory, well, who knows? Maybe in 100 years it might be the next revolution, right? Because I think to some degree, people in quantum mechanics might have felt that way at the time. So let's just look at this protocol in a little more detail. The way it works is Alice will choose one of 4 different states, and so we're using photons, so we're using polarized photons, and we can have horizontal vertical polarization states, or diagonal or anti-diagonal. And she chooses randomly which one to send. So what's important to note is that there's a correspondence between, let's say, the polarization horizontal vertical and the qubit state, right, 0 and 1. And now if I think of the diagonal polarizations like plus or minus, which can be seen as a superposition of horizontal vertical, these are the superposition states of this qubit that we're actually looking for or investigating to assess the security of the channel. So now Alice will send a random sequence of such kind of encoded photons. Just pick randomly one of the 4 states. And Bob now performs a measurement and can choose which basis. So that's a horizontal vertical basis or a diagonal basis. And if you just think of a polarizer, a polarizing beam splitter that is rotated 45 degrees or not, right? And Bob will get a measurement, like an outcome, which to Bob, it appears random because Bob doesn't know anything about Alice's states. It's only when they enter the next phase, they start a public discussion, which is the first step is called sifting. And what they do is they just determine for which cases did Alice and Bob choose the same basis. And those are the events they keep. So here's an example, vertical, Alice sends vertical. So if Bob happens to measure in the horizontal vertical, he will get the correct result. And likewise for diagonal state. And the other cases they discard, because what happens if Alice sends, let's say in this case, like horizontal, Bob happens to measure in diagonal basis, he will get a random result because those bases are mutually unbiased. So Bob's measurement has to be a random outcome, just based on the principles of quantum mechanics. And so anyway, they still a subset, which in itself will be random because Alice and Bob do random choices. But for those cases, Bob can get the perfect answer of what Alice sent because the measurements agree. So then what they do is they can associate certain states with a 0 and certain other ones with a 1. And that's how Alice and Bob will get a bit string. And if everything goes well, they'll be identical. They'd be random because they started off preparing them random, and then the measurement is random again, right? So it's a random subset, but they would be identical. And now to determine the security, what they do is they look at the error ratio. And why is this important? Well, if an eavesdropper tries to extract information or take measurements, these superposition states will start to degrade, and this will show up as errors. And in a very simplistic way, one could imagine the attacker is just literally taking taking those photos, doing a measurement, just pretending to be Bob, and then we'll resend photons based on that outcome. And it turns out, now this is sort of the most simple attack one could do, but in this case, the attacker would cause 25% errors. So 25% of the bits that Alice and Bob have in the end would be wrong, and so they can determine that just from a statistical analysis. Yeah, so that's kind of the in a quick way the ideas of quantum key distribution. This was the first experiment in 1989, so shortly after they put the protocol together, and now they implemented a quantum channel of 30 centimeters, and were able to demonstrate the protocol. And here, Alice was encoding the signals with a Pockle cell, which is an electro-optic modulator, and at the same time, Bob also had an electro-optic modulator to another Pockle cell to choose the orientation of the polarizing beam splitter. And yeah, like 30 centimeters. And so this is an overview of where things stand nowadays. It's already a little bit dated. This is from a review paper from 2021 from our Chinese colleagues, where they demonstrated a QKD network, pretty much over a large extent of the country. From particularly, they have a network from Beijing to Shanghai with lots and lots of nodes on the order of 30 or something, intermediate nodes put together with intermediate stations. And some of those bigger cities on the way, they have their own large networks that are branched out. And so they're able to demonstrate or build up secure keys over this vast network. They also have links to satellites, and we're going to that in more detail in a moment. And so ultimately, they're planning to reach the whole country. And here's a picture of some of the systems they have. There's a rack with lots of QKE, so quantum key distribution transmitters and receivers. For fiber optic systems, they typically work at telecom wavelengths, which is 50 nanometer, which is optimal for long distance in fiber. And here's a picture of one of their telescopes used for the satellite. So that is how this how it evolved. So why satellites? Why are we interested in doing this with satellites? And I'm switching over to this topic. Well, it comes down to the distances that we can mainly. That's the reason. So any kind of ground channel where there's losses that are absorption or scattering that are constant for any unit distance, it turns out there will be an exponential loss with the distance, right? Because you get equal probability for every unit. And fundamentally, that's where the free space transmission has an advantage. The loss of the distance will just go quadratic. Now, at first, this doesn't make a huge difference, but once you hit hundreds of kilometers, then suddenly there's a huge difference between exponential scaling and quadratic scaling. And so at least on paper, with the satellite links, one could do thousands of kilometers, millions of kilometers, even maybe. It's at least conceivable with today's telescope technology. And that's what makes it exciting. There's of course more. This is just one of the reasons why it's interesting. There's other reasons as well. If we just think of North America, in particular Canada, there's a large extent. It's a huge country, so we've got thousands of kilometers covered, right? And also, there's a lot of areas that don't have they wouldn't even have fiber infrastructure, for example. Crossing an ocean would be another reason of using satellites, because if we go 5,000 kilometers across an ocean, it will be difficult to have repeater stations and such on such an underwater cable. So there's several other reasons, and indeed with the Mitzios mission, our friends in China were able to demonstrate in 2017 satellite QKD. They launched a satellite in 2016 actually, and in particular they were able to demonstrate entanglement over 1,200 kilometers, and they did various demonstrations of quantum key distribution, also global, right? And a lot of the breakthrough demonstrations were done at the time. I will say now, there's now a lot of missions underway for other satellites for quantum communication. In particular in Canada, that's the one we are working on. But in many other countries, there's activities. So lots of missions in preparation. Here's an overview of some of the satellite quantum communication missions. This was in a paper, also around a review paper from 2021. And by now, I also realized just recently by looking at this again, so it ends at 2020. And unfortunately, this review, this picture, and one should expand it because there's actually quite a bit of update here that's not shown at the moment. What you can see is, so most notably here, the Chinese mission, Meteos is here. It was launched in 2016, and a lot of the major experimental results in 2017. And what we also have on this picture is the Canadian mission. Sorry, I'll just go like this. So we have, this is our Canadian mission, which was officially, so first sort of ideas proposed in 2014, officially announced in 2017. Another notable one entry is Cube, which is a mission in Germany, and that was actually launched August of last year, 2024. We are a part of another project with US partners, SEEK, which was actually just launched in November, last November, and it's now at the International Space Station and taking data as we speak. So that one, I should say that one, the SEEK is actually a enclosed box on the outside of the space station, where there's an entangled photon source and photon detectors. So our lab in Waterloo provided a photon detector system, but it doesn't actually have communication links. It's more like an interior enclosed experiment. But still, it is in space, and it's a stepping stone to testing these technologies in space. So there's a lot happening. And in my lab, in particular, I should mention, I came from fundamental experiments. Long distance, long distance bell test, long distance teleportation, like teleportation across the Danube and lots of other things, or new type of entangled sources. And after joining the lab joining Waterloo in 2009, I started working on more and more systematic sort of evolution of these systems, taking them from a lab setup, working with a lot of space industry, mostly in Canada, to show that the systems can be made robust, suitable for space, and essentially turn any kind of lab experiments into space suitable hardware. And here's a prototype of our system that's mounted onto an airplane. This is from NRC, the Twin Otter aircraft that they have based in Ottawa. And we used it to demonstrate our payload prototype on board of that airplane and linked to the ground, to a ground station not far from Ottawa. And of course, in our lab, then we've also been part of several actual space experiments and space hardware. And SEEK is already in space, as I mentioned, and the CSA QEYSSat project is underway. CSA is the Canadian Space Agency. All right. So that's our QEYSSat mission. Here's a picture. It's going to be primarily a receiver for photons. So this is a 25 centimeter aperture telescope, and we have photon detectors and photon analyzer. We can measure the polarization. And however, it will also have a secondary telescope that you can see here, and which can do laser communication, but also it will have a QKD source for sending signals to the ground. And if time permits, I have a slide about that. I could say more. So, but primarily it's a receiver, and that's interesting because the plan is we can send signals from the ground up, and on the ground have have a lot of flexibility on which type of quantum source we use, and therefore maximize the scientific sort of output. And we can test lots of different experiments, different sources, We're working with so here's a map across Canada, several partners to work on the science. Some of these, there will also be some of those partners with ground stations. Others have ground-based sources that we can bring to the station. And so actually now we have a large consortium of Canadian, as well as also, I should say, international partners, but particularly Canadian researchers. We have a large NSERC Alliance grant, actually, with 19 partners across Canada to work on topics related to this mission. So, and not just the hardware, but also theoretically to look at protocols and applications. We did a lot of modeling to get a handle of understanding of how good will this link, how good will the system perform, you know, what, and doing system or how do you say, hardware choices, like, you know, what wavelength, what telescope aperture sizes, and all kind of things were modeled. And so we determined that for QEYSSat, the best wavelengths, by the way. So here's a snapshot of absorption through the vertical atmosphere, and around 800 nanometer is somewhat of a sweet spot for uplink as well as downlink quantum communication, where the beam spreading and other aspects like detector performance, they all balance out, and so there's some kind of local optimum around that wavelength. But I will say that Telecom 1550 is actually also really good, and there's quite a few missions now in the works, which will study telecom. So the main reason for us why it wasn't relevant or not so interesting is because the detection at telecom is still tricky. There's really good detectors, which are the nanowire, the superconducting nanowire detectors. They're very good, but putting them into space is a bit of a challenge because they're big and bulky and cryogenic in particular. Yeah, so got some references so that anyway, this goes back to the early days. I already mentioned our airplane experiment. Here's a prototype of a detector module that we built with industry in a thermal vacuum chamber. This is the optical backend that we developed. And we also did radiation testing. A big issue is that once the detectors go to space, the semiconductor-based detectors, I should say, so we're using silicon in our case, the space radiation will cause a lot of dark counts from day one, you know. And so we did actually 2 runs of our prototype systems here in Vancouver at the Triumph radiation facility, and we simulated several years of space activity to get a handle on how good or how bad it will be, and to see what we can do about it, also mitigating the effects of radiation. So a lot of things have to be considered. This is a picture of our ground stations. There's several ground stations, as I mentioned. Here is one that is in the works in Waterloo. This is the north end of the Waterloo campus, and you can actually see the little dome here on Google Maps with enough zoom. And this will be what's called the secondary ground station for QEYSSat. The primary one is near Montreal, where the headquarters of the space agency is, the Canadian Space Agency. And so this will be the secondary. Yeah. Okay, so I'd like to now talk a little bit about some of the technical or maybe in a way scientific aspects that I've been investigating in addition to implementing this mission. And one of the interesting things we encountered was how to deal with the reference frame alignment. So what happens is when the satellite, or in this case, this is it's a night picture, a long exposure at night. That's why it looks a little bit weird of our ground station for the airplane, and the airplane would have moved over top, or the future satellite. And as the telescope is moving, there's relative rotation of the 2 systems, And also there is optical fiber running from this trailer. We have the sources in the trailer to the telescope, and all of that causes polarization rotation. So that means the reference frame of the sender and receiver are tilted and rotated. So what we did here is to perform a tomography measurement of the photons coming out, and then we apply 3 wave plates that can rotate, so we can correct the polarization in real time. So that works really well, but still, it's an extra system that has to run well. It has to be calibrated. So can we find some ways around that? And yes, indeed, we revisited some ideas from colleagues in Singapore and Bristol, where they proposed reference frame independent quantum key distribution. So what that is it's the best. Yeah, I don't have a sort of a fundamental slide here, but if you think of this entangled state, right, we have the 2 bases, 0 and 1 is our sort of computational basis, and we have a phase, and it's this phase that is drifting. And it turns out one can still do a QKD protocol, which is called this reference frame independent, where under the assumption that the computational basis is fixed, right, is not drifting or moving around, and only this birefringence phase here is drifting, one can still perform a QKD just based on analysis of the data. And the basic idea is simple. It's because even if you look at this, even if my phase is drifting, the entangled state will still be pure, right? It's just that the orientation of my basis would be off. And what they initially proposed was to use left and right circular polarization for a satellite link. And left and right circular polarization is obviously symmetric against rotation, right? Left and right circular stays left-right circular, even if you rotate, let's say, a telescope and a satellite relative to each other. And it's this phase that will change. So as long as the drift, so it turns out, as long as this drift is slow relative to the photon numbers that are received, one can actually work around. So we demonstrated that for entangled photons and in the lab, and now we used polarization maintaining fiber to send our entangled photons, which normally is considered a big no-no in the community. Also, when I myself, for many years, working on entangled photons, it was always, no, you can't, you must not use PMF. That was always the message. It turns out the polarization maintaining fiber, it has a lot of birefringence. So if one starts to analyze it and deal with that in a proper way, then one can still use it actually. So we implemented, we had an experiment. We have an entangled photon source, in this case, 2 such polarization maintaining fibers. We measure the photons. And now what is special though, one of the photons can be a 4-state analyzer for the polarization, like we have on our satellite. And the other one has to be a so-called 6-state analyzer. And we were able to show that even though one side is only a 4-state analyzer, we can still do the tomography that's required to assess the purity of the state, and so do a QKD. Now, why is this relevant for us? Well, this could be the satellite. It's a 4-state analyzer, and by doing this scheme, 6 states on the ground, sending the entangled photon to the satellite, we can get around this reference frame alignment problem. So that's the first one we're working on. There's the paper that we came up with, and we're right now in the process of implementing this on our Waterloo ground station. And actually, we worked on a QKD source that will go on the satellite, which uses this reference frame independent protocol in reverse. So here's a module that we built in our lab with partners from UK and also Honeywell, Canada. It's a small little box which has a quantum key distribution source with 4 lasers, and it will be connected. It will fly onto. It will be integrated onto QEYSSat, so it will fly with the mission, and it will connect to the telescope with such a polarization maintaining fiber. So the benefit now is that on board of the satellite, we can get this nice fiber optic link to our transmitter, but we don't have to worry about aligning the polarization on the satellite. So the complexity is taken away. And that was a major advantage here, right? So this is now, so yeah, this is now being delivered to Honeywell. It will be integrated, and if all goes well, it will be on board the satellite, and we can test it, the protocol coming down from space, with photons coming down from space. And oh yeah, and here is just recently in our lab, we demonstrated the system we mimicked. So in the lab, we have our source, and we simulate the quantum channel using, here's a blade. It can move in and out of the beam. So we use that to modulate the link attenuation. So what happens is when the satellite is passing overhead, the link first gets better, right? There's higher transmission. And as it passes over it, the satellite gets further away again, so the link gets worse. And we have a certain loss profile according to that. And we also simulate the birefringent that we could, birefringent effect of this polarization maintaining fibers. And so, yeah, we were able to demonstrate that it works. So this was done before shipping the unit to Honeywell. Another experiment we recently did is to investigate, so how can we connect the satellite link? So the satellite can reach long distances, but how can we connect it to a network of users on the ground? And so in our lab, we've been working on for a few years now on this nice project to develop an entangled photon source, which allows two modes of operation. So the source is on the ground, and in the first mode, when the satellite is available, which is only about a few minutes, right, for each night, in that mode, the source will send an entangled photon to the satellite, and the other entangled photon will be distributed to different ground sites, different ground users with spectral and also temporal multiplexing. So that will allow the end users, so multiple users on the ground, to establish a key with the satellite simultaneously. And then when the satellite is not available for the 23 hours and 56 minutes of the day, the same system, the same source will support a multi-user interconnectivity. So we can switch, in our case, a flip mirror, and the photon. So rather than sending the entangled photon to the satellite, it can be distributed among the network, and from wavelength and temporal multiplexing, the users will be able to establish a joint correlation and generate a key. Yeah, so there's a lot of simulation on this, and I should point out Stefan Binet has been working on this for quite some time now, did a lot of simulation and calculations, and the experiment is now wrapped up and been written up. So just recently we had a paper out summarizing all of the models and the theory. And for those of you working on photon detectors, there was a very interesting side result. That is that in the modeling, we thought, okay, why don't we assume we have the best possible detectors for the ground stations, which are photon number resolving detectors. And intuitively, it would seem that that will give an advantage for the QPD with an entangled photon source, because a problem with entangled photons from down conversion is you get the multi-pair emissions, which diminish the quality of the entanglement. However, it turns out that a regular bucket detector performs just as good. There's literally no advantage of the number resolving detector. There's only a very slight difference at very low losses, and that could even be due to the modeling errors. So we've been thinking a lot about how is this even possible, because it just intuitively, if I use a number resolving detector, I can really reject those multi-photon events, right? But it turns out that that's exactly what this model was doing, is optimizing the secure key. So what that does, what it means is, as you use a higher quality detector, yes, you're improving the visibility and the quality of your measurements with this number resolution, but your overall rate is going down because you have to reject more and more events. So there's just no advantage. So it has baffled us. For the longest time, I thought that's just some issue with the modeling. But we did find other papers where people simulated similar stuff, where they have little footnotes saying something like this might happen. And it's quite interesting. So I will say, though, this is interesting for experts, people using number resolving detectors in the field. But I thought it was an interesting side note. And encoding in other degrees of freedom has been a big topic or interest of my lab as well over the years. We spend a lot of time thinking about time-bin encoding for free space. So while building the satellite systems and the airplane prototypes and everything, we just struggled so much with polarization. And those of you who work with polarization in the lab, you will see every little element in your beam, doesn't matter if it's reflective or transmissive, can mess up the polarization. So building large telescopes and all kind of optics behind the telescopes for those satellite experiments, it's really painful to get the polarization rates. And so what about time-bin? Time-bin encoding, well known for fiber optics and well established, but in free space there's of course a problem. The modes get distorted, right? So there's turbulence, but also how do you align the reference frame? Because if you have two interferometers like Alice and Bob, they have to also be aligned, right? So that it would appear there's not really an advantage. But indeed, we were able to show that by using the same reference frame independent protocol, we were able to actually do a time-bin QKD experiment where the phase between the two interferometers can actually freely drift, and we can still extract the key. Because again, the same as before, right? Even just because the phase is off, as long as it's not drifting too fast, the states can still be pure, right? And by having a 6-state analyzer, here's a 6-state analyzer for one of the entangled photons, and the other photon was measured in a time-bin receiver. We can actually show that this works. And we also did it over a free space link and multi-mode fiber. So this is really neat, actually. There's an archive paper. And I'm nearly done, so just bear with me. Frequency bin encoding was another topic of interest. What about frequency bins, right? Actually, looking back at QKD implementations, even in the early days of QKD experiments, people noted that when you send the laser through a modulator, you get sidebands. Right? And they noted that those sidebands could be used for QKD. If they're weak enough sidebands, they're just populated with less than single photons, so that can be secure with secure comp. Okay, so what about frequency bins? Yeah, and they can be set up. You have two frequencies. You just make sure that the two frequency slots are distinguishable, and so one should be able to do quantum key distribution or any kind of quantum communication, actually. The challenge here is for free space links. So we're looking for satellites and free space, how to deal with a distorted beam, right? So this is a beam coming out of a multimode fiber, very bad and ugly. But by using compensated interferometers that we also studied for time-bin encoding, one can actually show that even though if this is my beam and this is an actual picture of the experiment, we have two frequency signals, and with such a compensated imaging interferometer, we can still split the computational basis perfectly, so we can actually extract this frequency bin information, and we can also look at the superposition, which shows up as beating between the frequencies. So that also just recently went on the archive. This kind of study, this is not a real QKD, this is just sort of a proof of principle. And I will say it connects to another experiment from earlier last year, mid last year, done by colleagues in Waterloo with quantum dots. They showed entangled. They looked at entanglement where the entangled state is oscillating because there's a frequency mismatch of the different decay processes. And so they have oscillating diagonal states or oscillating entangled states. But using very similar ideas as the reference frame independence, they were able to extract QKD or show that it can be useful for QKD, because just because it's oscillating, you can, and if you know the oscillation, you can still extract again the purity of those states. And and this relates to frequency encoding of quantum information. And with that, I just want to really quickly mention, so it's all about the quantum internet. So where do we go from here? So quantum internet is about entanglement distribution, right? So if we send, single photons or even entangled photons, but they are measured at the end, one can do QKD, but entanglement distribution is where it has to go, because that's when we can build a scalable network, connect to quantum computers or quantum processors. So that's the big vision. One of the what could it be useful for? One of the applications is quantum enhanced telescopes, where a few years ago with some colleagues, we looked at the scenario. This was, I should mention, Daniel Gottesman was definitely the main brains behind this project, showing that if we have an entangled state that's distributed between two telescopes, one can actually measure the state of the signals coming from an object in the sky, and perform a long baseline interferometric telescope experiment. Now, normally, in such kind of long those interferometric telescopes, they take a measurement and bring them together in vacuum tubes. But if we have entanglement that's provided by a quantum repeater network, when it's kind of turning the experiment around, so one shares entangled resources to the telescopes, performs local experiments at each telescope. And this could be a potential path or a use case to build larger baseline interferometric telescopes in the optical domain. Right now, it's still limited to about 400 meters, where they have actual vacuum tubes to bring the signals together. But if one day, in the future, when we have an actual error-corrected deterministic quantum internet, this could be one of the use cases. Of course, there's other applications, and ultimately it should go towards building quantum repeaters and interfacing quantum computers. And we want to build there's a dream, right, to build a quantum network across Canada, interface with quantum computers, such as the nice computers developed, here at SFU and at Photonic, with Steph Simmons and Daniel Higginbottom, and look at interfacing those kind of systems with long distance links, right? How would that work? And how can we build the quantum internet? So we've studied, thinking again of this Canadian-wide network, we studied all kind of link scenarios of lots of different altitudes and scenario and different scenarios like geostationary orbits even, or highly elliptical orbits, all kind of things. It's all written up in this QEYSSat 2.0 paper. But it turns out there's only, of all the scenarios one can dream up, only a few of them actually are viable, right? So here we have a plot of link losses and the time required for doing a useful experiment. And if just by making some assumptions on what's useful, one can exclude all of this over here, right? So the fun stuff like moon to ground station, right? Having an entangled source on the moon and distributing entanglement around the world, right? And a lot of other scenarios just don't work. What is very interesting to me is actually high altitude, so stratospheric platforms emerged actually as a very interesting intermediate ground where using high altitude stratospheric platforms as a relay between satellites and ground stations could actually really enable a lot of long distance distribution of entanglement, for example. And I will say ultimately, that's my going to the end. I think the future is for quantum. So we will have quantum repeaters. That's a big thrust of development. There's a lot of research. And I think ultimately we'll have hybrid systems of satellites combined with quantum repeaters. And there's several proposals out there already of putting memories into space and different types of memories. Here's one of the first endeavors in this direction came actually from joint work with Christoph Simon at Calgary University of having the satellites provide the entanglement link and the ground-based repeater nodes, which take those satellite provided models. And that we were able to show, interestingly, just with that simplistic model, that global communication could be done with just on the order of 8 satellites, 4 to 8 satellites, depending on orbits. So I'll come to the end conclusion. So yeah, first of all, it's all real fun for me. Realizing QKD systems is fun, but then building ultra long distance QKD systems with satellites is even more fun. So I spent lots and lots of years working on that, and I really like it. It's great. So a slightly more concrete summary as well. I think satellite technology will really enable quantum communication across Canada and globally. I think Canada is really well suited to be a user of that technology, given the extent of Canada and all of the remote areas in all kinds of directions that could be addressed with using satellites. And I should point out, with QEYSSat, the QEYSSat mission was actually pretty early on in it being a committed satellite mission. So I had this picture up of all of the missions going on, right? But pretty much at the time when the Canadian government said they will sponsor the satellite mission in 2017, there was not much else. The Chinese mission had just launched, and a lot of other proposals were floating around. But to make this commitment, I think Canada really stood up and stood out. So, and yeah, there's lots of work. And finally, there's lots of work to be done. I think we're only just at the beginning. The QEYSSat 2.0, there's conceptual planning already and ideas floating around. How to do teleportation across Canada as a buzz phrase. But this implies how to connect to quantum memories and quantum processor units to get this long distance entanglement into those stationary quantum processors. I think that's going to be one of the next big areas of research. And finally, I'd like to thank particularly my research group, all of the students and postdocs and staff working on this, and also a few logos of the various partners and collaborators over the years, which all help make this happen. So yeah, thank you very much.
Thanks for the exciting talk. Any questions from the audience? I can start from one question. So when you mentioned the d-square dependence of the satellite link loads, so what is the mechanism of that? Is that dispersion or other?
No, this is just pure optical beam widening. So
okay.
If you think of it as diffraction. Mm-hmm. So if you have an optical beam of a certain diameter, mm-hmm. it will, and if you have let's say a telescope with a certain diameter, the beam will propagate as if it was diffracted out of that opening. Mm-hmm. So if you have a large telescope, the diffraction angle is of course very small, mm-hmm. but it will still scale quadratic.
I see.
But however, it scales better the larger the telescope is.
I see. So if you make a larger telescope, it's much better. You can capture, yeah.
And it's like the resolution limit in reverse, if you think about it.
Oh yeah.
So astronomers want to have bigger and bigger telescopes because they can resolve objects in the sky with higher precision. And in reverse, the same is for a beam coming out of a telescope. The bigger the telescope, the better you can point it.
So can you have a larger ground station, so therefore your beam will focus at?
Conceptually, yes, but in practice, it's very difficult. In practice, because the atmosphere in front of the telescope will cause turbulence. So we for QEYSSat we analyzed it, and the optimal diameter is around 20 centimeter for sending an optical beam to space. But with adaptive optics and other methods, one might be able to make it bigger.
And there's essentially low loss during the atmosphere.
Atmosphere is not too bad. Yeah, like in this the graph I had. I mean, I will say it was a vertical, so as you slant, it gets worse. But it's 70-80% of transmission. So only 20-30% loss from the atmosphere. So it's not too bad.
Yeah.
Unless okay, assuming it's a nice day, or night, yeah.
Great. Any other question? All right.
So you have some variability in the source that we can use. Can you describe a little bit more what those options are?
Yeah. Yeah, exactly. No, that's so in the satellite mission itself, we define two sources. One is a so-called weak coherent pulse source, or QKD. That is a pulsed laser that is attenuated so it's less than a photon per pulse, and that can be used as one way to do the QKD. You know, the Alice photons that we saw, right? They can be implemented like that. And the other source that's defined is an entangled photon source, where we produce entangled photons from parametric down conversion and produce on the order of 100 megahertz with 100 million per second of pairs. And one photon is sent to the satellite and the other one is measured on the ground. And but so even there can be lots of different types of sources, like different approaches or technologies. And we have partners and collaborators with different sources. So same principle, but different approaches. And but fundamentally different would be to use single photon emitters. And we're working with some colleagues that have quantum dots in development, and they produce pure single photons. And it turns out for QKD that would be the best. So in terms of key per photon, in a way, yeah. So I'm trying really hard to find a collaborator who will have a source that is bright enough and strong enough, and at the right wavelength that we can use to send photons to QEYSSat. So there are some options around. And another source we're really hoping to investigate is a memory, quantum memory, where, let's say, so one option is to have entanglement between atoms and a photon traveling to space, or maybe even a photon that is, so the photon is entangled with a memory. Or at least using the memory as a single photon source. Now for that one, we already know that the rates will be very low. So if we can get a memory that matches spectrally to our satellite link, then it's probably just going to be a matter of, I have to admit, like showing proof of existence. We will not likely be able to do a real protocol, but I think that would already be a major step towards this quantum internet of interfacing memories with the satellite links. So yeah. Another thing we're investigating is with entangled photons. What's actually really interesting is when we have asymmetric entanglement, where one photon wavelength matches the satellite, and the other one matches the fiber optic telecom. And that's also actually beneficial because then one can get the best of both worlds. That's the idea. So the entangled source can be at the ground station. And anyway, the users will not be at the ground station. They will be away some kilometers or maybe even 10 kilometers in a city or some other place. And that's where the telecom fiber comes in. to transmit those photons, and the other one is sent to the satellite. So that's the underlying assumption in our internet networking scheme that I presented.
It sounds like some of these collaborators will already be in industry, not just academic research.
It's still mostly academic, but with partnerships in industry. Yeah. There are some startups. There's companies working on this, also big ones, with an interest in commercial QPD. They're of course very interested, and there's other partnerships. And in our EDSARC Alliance project, actually, there's several companies involved to be a part of those experiments. Yeah, it's great. It's exciting. It's been a long. I will also just say, I would just add, it's been a really long journey. I myself have been working on those ideas ever since I was a PhD student, like more than 20 years ago. And it's great to see this all finally happening, but it's been a long journey and a long time of working on it, where there was just a handful of researchers in the world at some point. But now it's a big area. It's lots of activity in this area.
Andrew from Victoria is asking a few questions. So his first question is, what is the end-to-end absolute efficiency of a photon pair from the source to the detector, given all the imperfections?
So he meant to the satellite.
Yeah, he meant the satellite. Yeah.
Yeah. For the satellite link, so that the photon that travels to space is around 40 dB of losses. So 10 to minus 4. So that means on the order of 1 in 10,000 photons will actually make it.
Okay, that's not that bad.
So yeah. But it's yeah.
Yeah, he also asked about you have a bullet point at the end. So there is quantum intellect in British Columbia. So that's he wants to know more about the current status.
This is just shaping up. We're just working on that. We're actually, and that's where BC Quantum comes in, right? Called Quantum BC. Yeah, we want to build some networking experiments around the city. There's some discussions going on of maybe getting fiber link or free space links horizontally. So that's essentially what this is about, right? So yeah, but it's still early days. The first step I can talk about is we want to establish line of sight from the SFU campus on Burnaby to the SFU campus in Surrey, for example. And we're also looking in, can we get a fiber link? And so we're just at the starting stage.
So that's how we can form the Surrey Darius office with a quantum secure communication.
Yeah.
And finally, he asked about, you mentioned about the application of those quantum satellites. So of course, QKD is one of them, and the other might be the quantum telescope you mentioned. So he also asked, is there any other quantum sensing application that you can envision that this kind of system would provide?
Yeah, quantum sensing itself. I mean, the main one that comes to mind is the clock synchronization. People have looked at that, or just using the correlated photons as an efficient way to synchronize clocks to the picosecond level. And that has been investigated, and that is one. However, that's not necessarily a quantum protocol. In a sense that it doesn't have a real quantum advantage over a classical correlated photon source, in that sense. But it's at the same time, it still uses down conversion, which is fundamentally quantum, right?
Yeah.
And it uses single photon detectors, which is also quantum.
Okay, still quite quantum.
Still, yeah.
Okay, so is there any one final question from the audience, particularly from students? No, students are shy at the beginning of the term. If not, for the sake of time, if you have further more questions, so send Thomas an email to ask more. But now let's thank Thomas again.